Hello, my name is Andrew Carter, and I'm the President and CTO of Resilience. At Resilience, we've developed health and integrity monitoring software for complex system of systems. Today, I'd like to tell you a little bit about our story, how we got started, the state of the industry as we see it, some of the challenges we've identified, and some of the solutions we're putting together, and then talk about how those can all be combined to a UAM system in Latin America drawn by Varen vehicles. So our background is that we were actually the developers. I was actually the architect of the Army's ground-based detect and avoid system. That system was deployed in 2016 for routine beyond visual line of sight operations in the U.S. national airspace. So the Army can actually fly whenever, wherever they want without getting any additional approval within the bounds of that system. That's kind of the holy grail for commercial aviation. It's what urban air mobility is trying to do. And so how did we get there? How did we do that? Well, in 2012, we actually had the system all up and working. And the FAA came in and said, well, how can you tell everything's working correctly? We thought we had a great answer for that. We said, well, we tested the system. We tested the crap out of it. And the FAA said, well, that's how you know it was working yesterday, but how do you know it's working right now? At the time, we didn't have a great answer for that. And then they asked, and what happens when something goes wrong? What happens when I pull this plug? What happens when lightning hits that sensor? And we didn't have a great answer for that either. It actually took us almost 3.5 years to re-architect that system to be entirely fault tolerant, to enable the FAA to put their stamp of approval on it and say this is certified for routine beyond visual line of sight operations. So then we've looked over, around that time in 2016, NASA was coming up with this whole concept of UTM, UAS traffic management, which has been kind of the underpinning of urban air mobility that I'll talk about a little bit later. And so when we look at the state of that industry, we didn't see anybody addressing this element of fault tolerance. We've seen a lot of research and development in UAS traffic management or UTM, and we started really to see that it's starting to transition from that research into the actual operationalization and commercialization. And urban air mobility is quickly following on the footsteps, following the heels of the UTM industry. Many of the same technologies, many of the same players are transitioning from, how do we integrate these small drones into the national airspaces, and then transition that to how do we do it in a more safety critical manner for the large passenger carrying or some more safety critical operations in urban air mobility. And so what we've seen is that the states and countries are starting to look at how they roll out this UAS traffic management. Public-private partnerships, or P3s, are starting to form. And we've seen air navigation service providers, or ANSPs, UAS test sites here in the US, and departments of transportation, and in some countries, departments of infrastructure, are really leading the charge in this area. But there's a number of challenges. We've seen a lack of performance specifications for the various services and capabilities. Many of those are in work in standards bodies throughout the globe, ASTM, ISO, RTCA. But really, there's no way right now for these industries to tell if the system is actually currently meeting the standard that they've actually been set up to meet. They can do some tests, they can collect a lot of data, they can develop a safety case, but it's not particularly scalable. A lot has to go into almost a one-off solution that doesn't necessarily translate to the next place that it goes, which is a problem for commercialization. We also haven't seen really the ability to detect off-nominal or adverse conditions, and then to mitigate those outside of a drone maybe going on the wrong flight path or losing connection. How configuration management is managed has been a large problem. These ecosystems are evolving very quickly, and yet they're safety critical. We've seen software, web-based software being changed on the fly while a drone was in the air. Obviously that's going to calm down a little bit as the industry matures, but it's still a major problem in the industry right now as we try to get to that operationalized state. And then fault tolerance. The FAA really beat into us that these systems have to be fault tolerant. They have to degrade gracefully. When something goes wrong, they have to fail safe. You need to be able to maintain some level of safety and capability when there are failures in the system that will occur with these cyber physical systems. And then how is contingency management handled? what we've really seen is that contingency management in a lot of the research and development has been focused primarily around the drone itself. If the drone flies off course, how does the rest of the operations handle that? But what we haven't really seen very much of is what happens when many drones in an area are relying on some capability. I'll use surveillance as an example. And that surveillance capability goes down. Those drones now no longer can see possibly what other manned aviation's in the area. And you really need more of a contingency management capability at an airspace level. How do we avoid some zone where we no longer have some aspect of our safety case that we thought we would have when we started our operation? Finally, maintenance of these ecosystems. Many states, countries, and DOTs are looking at, well, if we put up this infrastructure, who's responsible for it? Who maintains it? How do we reduce that time between failure, that MTTR? How do we get these systems? How do we remediate any of these issues that happen in order to get the system back up and running at a highly functional level, at a safe level, as quickly as possible? And so what we've done in Resilience to solve this problem is we've developed our solution framework, which is our fault recovery and isolation health monitoring framework. Framework monitors the health and the integrity of the various ecosystem components, anything from sensors to networks to C2, comms, nav. We bring in weather feeds, and we're really looking for how do we tell when there is some off-nominal or adverse condition within the ecosystem. Once we've monitored these things, we assess when we find something that's gone wrong, what is now the impact to the operations? What operations are impacted? Who could be impacted in the future? How do we shrink the number of operations that are impacted to the greatest extent possible? And that goes into mitigation. How do we mitigate the things that have gone wrong? Are there fault tolerance, graceful degradation techniques we can use? Can we restart systems to try to get them back online? Can we reroute traffic around areas that no longer meet the safety case that they signed up for when they started? And so currently we're deployed in 3 places: New York State, the UAS test range, the Ohio DOT UTM system, and the Ohio AFRL ground-based detect and avoid Skyvision system. And we're actually funded by almost every major federal agency in the U.S., including the Air Force, Navy, FAA, NASA, and Ohio Federal Research Network. And so what does having a system like Framework in the ecosystem do for you? It actually provides a fair amount of value, particularly in the area of safety. By increasing the system uptime and allowing you to tolerate these faults without having to report an emergency to your Civil Aviation Authority or ANSP, you can gain trust. You can say, hey, the system's not going to affect manned aviation. It's not going to rely on a lot of manpower when things are constantly going wrong. Autonomy, really, computers can only make decisions based on the quality of the data they receive. Understanding what quality that is and understanding what to do when they're not receiving the data they need is going to be a huge element of autonomy. They say garbage in, garbage out. If you're feeding computers bad data and asking them to make autonomous decisions based on that data, they're going to make poor decisions, and your trust in your system is never going to be the way where it needs to be for these systems to really truly take off. And that goes into the operator trust. When you're operating these systems, when you're riding on an urban air mobility vehicle, you want to understand that there's some level of safety assurance being provided and is constantly being monitored, and that there's a feedback loop to a supervisor or somebody that understands that when something goes wrong, a human can get involved and can help manage that contingency. And with maintenance, maintenance is always an issue. The O&M costs of these large ecosystems are going to be enormous. So how do we reduce that as much as possible? Looking at automated root cause analysis, digital logistics, and doing preventative maintenance on some of these systems as the ecosystem grows. That goes into the whole airspace safety. In-time system-wide safety assurance, a term that NASA has coined, to look at how do we provide the safety assurance across the entire ecosystem. How do we make sure that all the bits and pieces are working correctly and are communicating? And then how do we get information to an operator when something goes wrong in time for it to make a difference. Currently in manned aviation, a lot of the safety assurance practices are done post-processing. Data is aggregated, is sent back, is analyzed, is post-processed, and really the feedback loop is back into the design change process. We really want to shorten that feedback loop in time to make a difference during the operation versus months later during a design revision. Finally, what capabilities are still available? This is really important for operators to know. If something does go wrong, how much flight time do they still have? What areas are still available for them to fly? Is it safer for them to get out of an unsafe area or to land immediately? Do they need to go home? Knowing what capabilities are still available versus what is not is going to give them the ability to make decisions based on that. So I talked a little bit about in-time system-wide safety assurance. This is really kind of what we're talking about here. Is in-time system-wide safety assurance is not necessarily some monolithic module inside of this architecture. It's really a layer around the entire ecosystem, where these monitoring, assessment, and mitigation capabilities may be a part of a USS. They may be a part of onboard the drone itself. They may be a part of the ground control station. In our case, we provide some of these capabilities as a supplemental data service provider. But really, we aggregate bits and pieces that come from all aspects. A lot of European and countries that have a privatized ANSP are doing more on the FIM side, the Flight Information Management System side, to provide some of these monitoring, assessment, and mitigation capabilities. So how does this fit into a UTM and what will eventually turn into more of an ATM or UAM architecture? So here we have just kind of a generic architecture with many of the functional blocks that have been identified through various standards organizations throughout the world. And this is just an example of what one might look like. What we've seen in just about every single instantiation of UTM across the world is that there's some kind of operations and control center. Somebody wants some oversight. They want to understand what's going on, have some situational awareness about the airspace. They want to be able to store data for, if something goes wrong, how do they do event recreation? How do they do analysis to understand, what's going on within their airspace? They want to be able to do that data analytics. They want to control and manage the airspace. They want to be able to say, this airspace is now off limits because X, Y, and Z event is going on. Maybe there's a football game and we can't fly over, a stadium today, or a president's, going through, and we don't want any drones near that presidential parade. Operations management, a lot of agencies that we've seen that are implementing these have their own operations. So they want to do some element of fleet management. They want to understand where their own operations are and where other operations are and be able to deconflict those. Situational awareness about the airspace, but also about the systems that are involved. Are the systems that are making up this ecosystem actually operating correctly? Are they having any kind of degradation? Are the networks all working? Latency is a big problem when you start to talk about web-based software and large-scale networks and tight latency budgets for making decisions in the air. I mentioned maintenance. As you get into this operations and control center, that's going to double as a maintenance center. They're going to need to understand what components are working, what components are down, putting in tickets to fix things. Can they control or restart or do any kind of maintenance debugging from the centralized control center? And then wide-scale contingency management. When things go wrong in these ecosystems, there is going to be a human that gets on the loop. Even in the case of highly autonomous systems, there's probably going to be some element of human oversight at a high level for when things go wrong. Some comms network is down and now all the systems have to switch over to a backup system, or they're going into lost link procedures and they need to deconflict the airspace. There's going to be some element of contingency management at a control center level as these systems move forward. Now in urban air mobility, that may look, a lot of this operations control center may look like a vertiport. Each individual vertiport may have all of these functions and may control some area where they're doing contingency management and they need situational awareness about incoming and outgoing flights. Are the systems at the vertiport working correctly? Is their battery charger working? Is there, do they have landing pads open? Do they have systems that can automatically get people in and out? Is security up and running? Is there systems that are doing flow control for the incoming and outgoing flights working? So we see as this transitions from UTM and UAS traffic management for primarily small drones to really getting to more of a vertiport being a kind of a mini airport of sorts that has these type of capabilities for the surrounding localized airspace. And so how do we play a role to this? Resilience is really providing situational awareness about the system itself, maintenance capability, and contingency management. So we're looking at how do we give an airspace operator or a maintainer the ability to understand the state of the system, what it's doing, what it's not doing, what capabilities are available, how that's affecting operations, and are there any procedural or automated mitigations that they can inject into the system to try to remediate the situation or reduce the impact of these adverse or off-nominal conditions. So how does that affect what Verint Vehicles is doing in Latin America? We think that they've done a fantastic job of really simplifying the system. These systems are going to get complex. Complexity obviously, adds time, cost, regulation, and is going to slow down the adoption of these ecosystems. So by reducing the complexity to the point that they have, we think that they've really put together a system or concept that's going to gain traction quickly. But there's still going to be an element of complexity. It's going to be many moving parts, especially when you talk about how safe the system needs to be. When the level of safety goes up, the level of risk mitigation goes up, and generally risk mitigation is going to add complexity. Some of that risk mitigation can be procedural, which we think is going to be a large part of the early adoption. But as you get more automated, as you want to, drive the cost down by getting more of these computers involved, you're going to see a lot of safety assurance capabilities that have to play into the ecosystem. So we're excited to work with Verint Vehicles in Latin America and worldwide, and we think that bringing safety assurance capabilities to this ecosystem is really going to accelerate their adoption, and is going to be a huge deal for the certification authorities that are involved and want to understand, again, how can you tell everything is working, and what do you do when something goes wrong? We're Resilience, and thank you for your time.